All right. So, happy sixth snow day. Today's lesson is section 7 in chapter 7 in your textbook, and it's entitled Numerical Integration, or Integration Methods, or integral approximations, or something along those lines. And we're going to look at something a little familiar and something a little different. The thing that is familiar is a Riemann sum. Okay, so I know that we've already sort of talked about the midpoint rule, but what we want to look at today not only is the midpoint rule, but we're also going to look into the trapezoidal rule. So just as a reminder, well, today we're going to be playing with this function almost exclusively. Okay. So as a reminder, the midpoint rule is where I would take my subintervals up to where the middle of each subinterval intersected the function, and I'd add the areas of those up. In the trapezoidal rule, which is the new one that we're going to look at, we go all the way up on both sides and make a trapezoid. I know that might be hard to see. But there are some good pictures in your textbook about for this section. So, all right. So what we want to do is we're going to use both the midpoint and trapezoidal rule to integrate this guy. Now, we know how to integrate this. This is just the natural log of 1 minus the natural log of 2. Oops, backwards. The natural log of 2 minus the natural log of 1, which is about 0.6 something, 69315. Okay, and we'll come back to that actual value at some point as well today. But we're going to look at first calculating the integral approximation with 5 subintervals. Okay. Oops. So this is a numeric integration. The reason the section is called numeric integration is the midpoint rule and the trapezoidal rule are all algorithms, and your calculator is very good at doing algorithms. So all of these problems could be done very easily on the calculator, and actually this particular problem that we're doing today, you would need a calculator to calculate, obviously, like the natural log of 2 and the natural log of 1. But let's think first about what this midpoint thing means. Let's put another tick mark here. So that we can sort of have a Now this isn't drawn to scale, but we can kind of see a 1 to 2 with 1, 2, 3, 4, 5 subintervals. Okay. Well, what we want to do is add up all the areas of these 5 rectangles. Well, each rectangle is going to have a width, and that width is 2 minus 1 divided by 5. That's delta x. Okay. And then the first rectangle is going to have a height equal to the value of the function at 0.5. Excuse me, not 0.5. This is 1.2. This is 1.4. This is 1.6, 1.8, and then 2. Then halfway between 1 and 1.2 is 1.1. Okay. So the area of the first rectangle is 1/5 times f of 1.1. The area of the second rectangle is going to be 1/5 times f of halfway between 1.2 and 1.4, which is 1.3. So on and so forth. You can see that every one of these terms is going to have a factor of delta x in it. So I'm really just saying 1/5 times the sum of all of these midpoint values, which can be easily determined on your calculator if you type 1/x into y equals, and then set your table up to give you those values. Okay. And then you could use your calculator to do a summation, add those values up, and then multiply by 1/5. So. All right. And this approximation comes out to be, what was it, 0.692. Okay, so don't forget the question app. If you have questions, please post a question and I'll get to it when I see it. So here would be our estimation of the midpoint rule, or using the midpoint rule, our estimation of the area under the curve from 1 to 2. So coming up with the general rule for this. It's just delta x times f of x of k. What do they call it? F of x of 1 bar. Yeah. F of x of 1 bar. F of x bar 2 to the dot. Okay. Where the x bars are just the average or the midpoints between intervals. Okay. Okay. So the next thing we want to look at is, obviously with this estimation, there is some error that comes into play. And what's called the absolute error is simply the absolute value, the difference between the actual integration or the actual area under the curve and the estimate. So the absolute error. And I have that as, so that's pretty good. That error is pretty good. There isn't too much. So this is a decent approximation. Okay. All right. Now let's look at the trapezoidal rule. I'm going to leave a lot of this stuff up here. We want to do the we're going to keep track of these errors. We're going to do the trapezoidal rule, and we're going to look at the error for that as well. Okay. Trapezoidal rule we're going to do in blue. Because trapezoids are STAD. Because they only have one pair of parallel sides. Okay. So, I should be how to spell trapezoid. Now, there's another rule in your textbook called Simpson's rule, but we won't look at that. That's not something that we concern ourselves with. All right, so the trapezoidal rule, the first thing that we need to do is remember what the area of a trapezoid is. Right? A trapezoid with two bases and a height has an area equal to 1/2 the sum of the bases times the height. So how do we translate that to what's going on over here? Well, first of all, these trapezoids are turned up this way so that the parallel sides are these. Okay. Which makes my height dx. Okay. And the bases are just the values of the function. Okay. So we do need a dx. Same thing, 2 minus 1 over 5 to the 5th. So that's my h. Okay. So notice that the area of each of these trapezoids is going to have a factor of 1/2 and a factor of h. So I'm going to pull those out. Now what I have to do is add up, oops, it says B1 or B2, B2, we want B2, B1. I need the sum of the bases of this trapezoid. Okay. So the basis for this trapezoid, trapezoid number 1, the large base is going to be f of 1, and the shorter base is going to be f of 1.2. Now, moving over to the next trapezoid, the larger base is f of 1.2. So we really have two of these. and then f of 1.4. Moving over to the third triangle, f of 1.4 is now the bigger base. So we have two of those. This base is only ever going to be calculated in here once because it's not the big base of the trapezoid next to it. It's just the small base so we get something like this. And again, this can be calculated numerically on your calculator by using tables. But for our purposes here, it is about 0.696. Okay. And by the way, the notation that we'll use for the trapezoidal rule is a large T, and the subscript represents the number of intervals. Midpoint rule with 5 intervals. So let's see, my absolute error about 0.003. It's a good, we'll do this. Because I like 3 decimal places for answers. The only reason I went out so far with this one was so that we made sure that these answers came out to be accurate. Okay. So the absolute error there we go. Nope, you can't see that, can you? Let me get rid of this. You all know who I am. Oops. Okay, and that's it for the old stuff, the familiar stuff. Now let's look at something a little bit new. Still involving midpoint and trapezoidal rule, but looking more at this error stuff here. Okay. A lot of times, especially in engineering, we ask ourselves, okay, how much work do we need to do to be within a certain realm of accuracy? This is called error bounding. We want to bound our error. Okay. So let's look at the midpoint first. Sorry, I can't decide what color I want to do this in. So what if I want my error to be within okay. I want my error to be within 1/10,000th accuracy. How many subintervals would I need? And that's the answering the question of before when I said how much work do we need to do to be as accurate as we might want. Because obviously for these problems, the more subintervals you have, the more work you have to do, or in some cases your calculator has to do. But regardless, same conceptually, same idea. So what we're going to use are two formulas. The first one we're going to use for the midpoint. And they're actually, I mean, we can write them the same. If I can find the value of the second derivative, or excuse me, if I can find a value k that is greater than or equal to the absolute value of the second derivative for all values of x on the for all x in a to b, could be a, could be b, then we say that the error in the midpoint rule is less than or equal to k times b minus a over 24n squared. Oh, sorry, this is cubed. K times b minus a cubed over 24n squared. Now, typically that's something that's given to you on a test or a quiz. In the AP test, I believe they give you those, the equation for the error bound, which is nice. And the error for the trapezoidal rule is very similar. Here are the two differences. So if you did have a quiz or a test where that wasn't given to you and you were trying to come up with some error, you were trying to do this on your own, they're not hard to memorize. There's just two differences. Oh, there's only one difference. I thought this was squared. I could have sworn that was squared, but it's not. It's cubed. Which means there's only one difference. Okay, so we're going to answer this question for this problem here. What value of n do I need? Or in other words, how many subintervals do I need so that the midpoint rule comes within this error in the trapezoidal rule is within this error here. Okay, so the first thing I need to do is find the value of k. Okay, and for this theorem, it said that k, if k is larger than or equal to the second derivative, so we do need to find the second derivative of 1 over x. F prime is negative 1 over x squared, and f double prime is 2 over x cubed. Yeah, I think so. Yep. Okay, so let's think. We'll sketch here. 2 over x cubed kind of has this situation going on. It's always decreasing. So the maximum value, which is essentially what this is saying, is find a value of k that's larger than the second derivative on the interval from 1 to 2. Well, it has to be the case that the maximum value of this occurs at 1. Okay, but we'll test both endpoints. If this were something that might have peaks or valleys in it, then you'd have to do a check for maxes and mins or local relative extrema on the interval. But we're lucky because this is always decreasing because it looks something like this. So we know that the maximum has to occur at one of the endpoints. Okay, and specifically it has to occur at 1. But let's just double check. So f of 1 is 2, and f of 2 is 2 over 8, which is a fourth, right? So this is the biggest. That's what will make k. Okay. So now I know k, I know a, I know b, excuse me, I know a, I know b, and I'm solving for n. Okay. So we want the error to be this. K we're going to make 2. B minus a is 1. Okay. So n for midpoint was 29. So n equals 29. So 29 or more subintervals would give me an error within this bound. Oops. All right, let's try the trapezoidal rule. It should be very similar. Let's see, 0.0001. 2 times 1 over 12 n squared. N is going to be the square root of 2 over 12. Okay, and we would expect this value of n to be larger, and it is. It's 41, roughly. If you get part of a subinterval, round up, because if you round down, then you're not going to be within your error. You're going to have more error, right? Because for instance, this answer comes out to be, I believe it's like 40.8. And so if we said, oh, 40 subintervals will do it. Well, no, 40.8 will, but you can't have 0.8 of a subinterval. So you have to go up one more, okay? Or these bounds, these aren't exact figures, right? I could make k as large as I want, right? I could have made k 12, right? That still satisfies the hypothesis of the theorem. 12 would be bigger than the second derivative anywhere along the interval from 1 to 2. It's just going to make these numbers really big, okay? I wanted to know what's the smallest number of subintervals required to get me that error, and that would be those two values. Okay. Now, think about this. This makes sense because look at the errors over here. When we did the absolute error for the midpoint rule, we got 0.001. When we did the absolute error for the trapezoidal rule, we got 0.003. So the error was worse with the trapezoidal rule. We had more error with the trapezoidal rule. So we would expect to need more subintervals to get within that error. All right, so that's it for today. And actually, that's it for chapter 7. So for those of you who are logged on from my class, the quiz is still scheduled to be next week, whenever we have class next. And then probably what we'll have to do is continue moving on into the next chapter. Nothing from the next chapter will be on this the semester, but we'll move on to give you some time will give me some time to grade the quizzes, get them back, talk about them, and give you some time to review for the test, but we'll still try to have the test by the end of the quarter. And then we'll talk about what to do with test corrections and stuff, but I don't like putting, like, this entire unit's been in this quarter, so the test should be in this quarter. But we can talk about that next class. Okay, that's it. If you have any questions about what we talked about today, feel free to email me. Yeah. Enjoy the rest of your snow day and your Friday tomorrow and your weekend, and I'll see you, I don't even know, Monday or Tuesday. So take care. Sophie asked if I'll post the notes to Blackboard. Yes. Yes, I will. Everything is posted to Blackboard that you need to perform well on the quiz. And I will post notes, if not by today, definitely by the end of tomorrow. So, good question.